So we've looked at indefinite integrals and antiderivatives, and now we're going to get into the part where integration represents area under a curve. So in normal calculus courses, you go a little more in depth than what I'm going to do for area under the curve. I'll explain kind of the fundamentals behind it, and we'll look at a couple examples, but we're, like I said, not going to get as in depth that you might get into in a different course. Definite integrals is tying in derivatives, antiderivatives, area under the curve, and is fundamental theorem of calculus comes out of that. Okay, so area under the curve. So if you're looking at, let's say you had some equation, you had a function f of x, and it was continuous, and it was above the x-axis. Let's say you bound this. So let's say you have some value a here, and you have some value of b here. And you want to find the area bounded between A and B. So right now we don't know how to do that, but we know how to find areas of shapes. And so if we could make this into shapes that we know how to find the area of, then we could get kind of an estimate of what's going on. And so what we're going to do is we're going to break this up into rectangles. And so there's 3 different ways that we can break this rectangle up. We can make the height being the left-hand value of your function. So let's, for instance, if I put a point here. So let's say I want to break this up into 4 rectangles. And so I would take this, I'm hitting my function on the left, and I'm going to go all the way over and make my rectangle. So if I hit my rectangle, that's where the height's going to be on the left, and going over to, oops, my other x value. So again, you're going to hit the function on the left that is giving you the height of that rectangle. So basically, by doing this, we took this distance, and we can find that distance between our 2 bounds, A and B, by taking the larger bound, B, and subtracting A. So that's the length of between the area that we're looking at. And in this case, I subdivided this into 4 different intervals. And so if I divided this by n, where n is equal to number of intervals, you break up between A and B. Then B, then B minus A all over n. This is equal to the length of each interval. So in our case, if I was looking at it, because we split it up into 4 different pieces, this length in here would be whatever B minus A was divided by 4. So this is actually, in our case, equal to the width or base of our rectangle. Of one rectangle. And we know we can find the area of a rectangle, right, by base times height. So the area of the rectangle or length times width. And so we basically just have the width of our rectangle, and to find our heights, basically we could just look at what this value is of our function. So right here, that height, this is f of a. So if I knew what my equation f of x was, I could plug in that x value in to get me that height here. Same idea here. So sometimes we'll call this x of 0, x of 1, x of 2, x of 3, and x of 4. So to find the height of the rectangle between x of 1 and x of 2, I would just plug in my x value there, f of x of 1. So I could find the area of each one of these rectangles. If I find the area of each one of these rectangles and we sum them, then we're going to get an approximation of the area under the curve. Okay, so notice if you take that and you split it down into more rectangles, the more and more rectangles that you put underneath that curve, the better estimate that you're going to get. And so the process, kind of similar to what we were doing with limits or derivatives, when we were trying to find the rate of change at a point, we tried to choose those points closer and closer together so we could get exactly what that rate of change was at any point on a continuous function. That was differentiable. Same kind of idea here. This time though, we're gonna put an infinite number of rectangles in there. And by doing that or making that go off to infinity, we're gonna get an exact estimate of that area under the curve. Okay. So let's take let me just rewrite that curve. So again, we got some value A, we got some value B. We want to split it up so that we can find the area under this curve. So the more rectangles, the better estimate. Okay, so let's say we took one of these rectangles outside of our curve and just kind of talk about it. So we are going to call this value in here. That, remember, is the length. So B minus A, the length of the interval that we are finding the area of, divided by the number of rectangles we're trying to get. We're going to call this delta X. That width of our rectangle keeps changing. It's a change in our X value. So here, this is delta X. So any rectangle that we pulled out from underneath that curve, that would have the width of delta X. And so from here, let's just choose some arbitrary value. So it ends up that at the beginning, when you're looking at this, we either choose a left endpoint for our height, or the right endpoint of the curve of that rectangle for our height, and the other one is a midpoint. So the midpoint in between there. But if you're getting those rectangles infinitely closer together, it really doesn't matter where you're choosing that value. And so we can choose technically any value in between this rectangle to get the height of the base of that interval, to get the height of that rectangle. So we're going to call this right here, this f of x sub k. This is equal to the height. Rectangle. Okay, so if we take the width and the length, so we have this f of x sub k, or the height, times the width, delta x. But that's just one of them. And so basically what we have to do is we have to sum every single area of each rectangle. So if we sum each rectangle, as n goes to infinity, we will get the exact area. Under the curve. F of x. Okay, I'm putting a couple stipulations on there, and I'll explain why in a minute. But that curve f of x has to be above the x-axis, greater than or equal to 0. Can touch the x-axis. And then also it has to be a continuous between A and B. Okay, so here we go. We can say if we look at the limit as n approaches infinity, so more and more rectangles of this jagged kind of E is a summation notation. And so that's telling us that you're summing all these terms. And we're looking at when k equals 1 to n of f of x sub k, the height of the rectangle, times delta x, the width of the triangle. So you don't have to worry too much about that, but that's basically saying that we're just summing each one of those rectangles, and that's what that notation is. And that n is saying that we're making that go to infinity, so an infinite number of rectangles so that we get an estimate. This actually translates into what we were doing before with the integrals. So this summation, we're integrating, we're summing basically, and that's maybe why that integration or integral looks like that. We're summing f of x. So we're summing all the rectangles. And this dx, this is our change and the width. So that right there is an indefinite integral, what we were looking at before, but now we have this a here and we have this b. So we have a number on the bottom of our integral and we have a number on the top of our integral. And this a value, this is saying right here, is this is where we're going to start. So the start of the bound of the area under the curve. And this b value, this is the end bound. Okay, so I'm going to just kind of skip. Okay, so let's look at an example or some examples real quick. So let's find the area. Or estimate, find the approximate area. How about that? Right, approximate. Area under the curve. Using shapes. Okay. So we have a graph. And my y-axis, I'm going to go up. Okay, so I have a point at 0, 2. I'm going to have a point which is at 2, 3. I'm going to come back down and have another point at 4, 3. And in between at 3, I hit a max of 3.5. So far we have this following curve. And then let's say we come back down and we hit a point at 5, 1. That's a minimum. We come back up at 6, 5. We hit a point at 7, 5.5. And we come back down and have a point at 8, 5. So let's say it says approximate, which I already said, the area under the curve using shapes, and let's do rectangles and let's subdivide it into 4. 4 rectangles. Okay, so we're trying to find this area. We want it in 4 rectangles, and so we have to look at what the width of a rectangle is, and we can call that the change of x. So this is the larger bound 8 minus the smaller bound 0 over how many rectangles we want in this case, which is 4. And so this is going to give me 8 divided by 4, which is 2. And so that's telling me each width in here is 2. Now we got to determine, do we want to hit the left, the right, or the midpoint in between these? And it really doesn't matter. If we do the left one, usually actually the right one is the easier one with calculations if you had to do this. So maybe we could use the right one. And we had shown the left one before. So if you're using the right point, this is going to give us a look at the end value of the first interval, which is at 2. You're going to hit the graph there. That's going to give us the height. And so we need to look at the height there. So f of 2 gives me the height, and we're going to say that's 3. Times this base. The base, though, is 2. So plus. So if I'm doing the right-hand bound, I'm going to hit 4. I'm going to go up on my graph. That's where it's hitting the graph. And so I'm going to make my rectangle, and that's going to be the height. And so f of 4, notice f of 4 is 2. So the height is 2 times the width, which is also 2. Plus, so if we go to the right-hand endpoint, so that's at 6, we go up to the height of that. So doing that, f of 6, we can see f of 6 is at 5 times the width of 2. So now going to our height of our last rectangle, painting our curve here, and then going over. Oops. So we would look at what f of 8 is. F of 8 is 5 times 2. So basically with this, we're looking at this area in here. So this is an overestimate because we're above the curve. We're looking at this area of this rectangle in here. This is kind of an underestimate because it's below where we were looking at the area. This one's an overestimate. It's above where our curve is. It's a little bit of a underestimate. But if we did this and put it all together, we get this as approximately, well, this gives me 6 plus 4 plus 10 plus 10. So this gives me 10 plus 10 plus 10, so approximately 30. I don't know what my units are, units squared. Okay, so if I broke that down into 8 different rectangles, I would get a better estimate. So notice if I didn't put the stipulation that that function had to be above the x-axis, when I was looking at f of an x number, if I was looking and it fell below the x-axis, that would give me a negative number. And so negative times the positive, that would tell me my area is negative. And so that we have to take that into account. So we will look at the cases where we're looking for area and that function does fall below the x-axis. Then we're going to have to look at that piece below the x-axis and take the absolute value of that piece if we're looking at area. So let me give you some properties of these exponent or these integrals. So properties of definite integrals. Okay, so if you were looking at a function, f of x, and you were looking at the integral from some value a to a, what do you think that is? What do you think the area is from a to a? It's actually going to give you 0. If you were looking at the integral going from b to a, we're putting on the stipulation that b is bigger than a. So if our lower bound is bigger than our upper bound, and we're taking the definite integral, this is going to equal the negative of flipping our values a to b of f of x dx. If we're looking at definite integral from a to b of some constant c times a function f of x dx, we can bring our constant in front of our definite integral and then just integrate f of x from a to b dx. If we have summation, just like we did with the indefinite integrals or subtraction between terms, think of it as multiple functions. We can break this down as the integral of the first function from a to b, plus or minus the integral of g of x from a to b. Sometimes it's necessary that we break down our integrals. So let's say our bounds were from a to c of f of x dx. Sometimes we might have to split this up into 2 separate integrals. So this is the same thing. We can go from a to b of f of x dx, and then add on the piece from b to c, f of x dx. Where we're saying that b is between a and c. Okay, so a case that we might want to do that is, like I was saying, if your function falls below the x-axis, if we find out where it's falling below the x-axis, that's where we would want to split up our integrals so that we could take in fact that we want the absolute value if we're looking for area underneath the curve. Okay, here you guys go. Actually, okay, let's just do it. So the fundamental theorem of calculus. We can find an area under the curve. This is equal to our integral from a to b of f of x dx. So remember our antiderivative, we denoted with a capital letter of whatever our integrand was. And so little f of x, we would denote it with capital F of x. We have to say that f of x is greater than or equal to 0. We have to say that f of x is continuous. On AB. Then we would write this, the antiderivative, we would denote it with a vertical line of our bounds a to b. This is equal to plugging in your larger bound, the top bound, into your antiderivative minus the lower bound of the antiderivative. So in here, we don't have to add the c. Because if we did, basically, if we added a plus c here, we would be subtracting it off here, and they would undo each other. So we don't add c for definite intervals. So let's kind of just look really quick why we would subtract that off. So if we, again, we're looking at some curve, this was A to B. That definite integral, if we are looking at it, it's basically looking at from f of b, this is looking at the area from here to here. But the f of a, what we're doing is we're subtracting off this area in here would give us that total area that we wanted. Okay, so let's apply this. Let's actually go with an easier function. Let's actually really go easy. How about 0 to 5 of x dx? Okay, so by this rule, we want to take the antiderivative of x. And so if we take the antiderivative of x, remember the rule says we're adding 1 to our exponent. So we have 1 plus 1, which is 2. And we're dividing by our new exponent of 2. And we're evaluating this from 0 to 5. So we're looking at plugging in. So we're looking at f of 5 minus f of 0. So we have plugging in 5 wherever we see an x in the antiderivative minus plugging in 0. So this would equal 5 squared, which is 25 over 2 minus 0. So this is equal to 25 halves. Or 12.5. Okay, so the reason why I wanted to do the easier one is, now let's just look at the graph of that. So if we were to graph f of x equals x, so whatever your x value is also your y value. So when x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 2. I probably didn't give myself enough room. Okay, so we got a straight line there. Pretend. And if we were looking at, now look at the area. So if we looked at the area bounded by the curve, and the x-axis, between 0 and 5. So basically, that's a right triangle. And we can find areas of triangles. So an area of a triangle, well, this is 1/2 times your base times your height. Okay, well, using our knowledge, this is 1/2 times the base. Well, this length in here was 5 times our height, and our height is also 5. So our area is equal to 25 halves, or 12.5, which is the exact same thing we got by using the definite integral. Pretty darn cool, right? Okay. Let's look at one more before we take a break. And again, I want to kind of look at one that we already know how we could figure out what the area is really without using definite integrals. But let's first show it with, let's show it both ways. So what about the integral? Actually, can I do that? Maybe let's take a break, because there is one example I wanted to do, but I don't have it right next to me, and I don't want to mess it up by putting something different down. So let's go ahead and take our break now, and then we'll come back in 10 minutes. Let me pause this. Okay, so let's go over a couple more examples where we look at the fundamental theorem of calculus, the definite integral, and looking at finding the area under the curve by using our knowledge of shapes. And so let's look at the following. Let's look at the integral from 0 to 3 of 9 minus x squared dx. And so let's first evaluate this using definite integrals. Okay, so doing that, we can break it up where we can take the antiderivative of 9. The antiderivative of 9 is 9x minus the antiderivative of x squared. So remember, we add 1 to our exponent, so it's now going to become an x cubed, divide by our new power, which is 3. And we're evaluating this whole thing from x equals 0 to x equals 3. So we're technically looking at what is f of 3 minus f of 0. So if we go back into our antiderivative and we plug in 3 wherever we see an x, we have 9 times 3 minus 3 cubed all over 3 minus, be careful here, in this case it doesn't really matter because we get back 0, but if you have more than one term and you're plugging in that number, that negative is going to every single term. And so now plugging in 0 wherever you see an x, so we have 9 times 0 minus 0 cubed over 3. So we get 9 times 3 is 27, minus 3 cubed is 9 divided by 3. Okay, so 9 divided by 3 is 3, which gives us back 24. Did I do something wrong?
I don't think 3
Yeah,
cubed.
that's 27 divided by 3, which is 9. Thank you. Okay, so 3 cubed, which is 27, divided by 3, which is 9. And 27 divided by 9 is 18. Okay, well, let's look at this. We are now wanting to, let's graph f of x equals 9 minus x squared. If it helps you, we can rewrite f of x as y. Okay. Let's not graph that because I did pull out the wrong column when I was thinking this. I was thinking this was a semicircle, but that's not because it's y squared would be equal to that. So let's actually, we're not going to do looking at the area of that one under. Sorry about that. I do want to look at one more though. I know this one will work. Let's say you have f of x. This is equal to 3 minus x. And we want to sketch a graph of f of x. And we want to find the area between the x-axis and x equals 4 and 8. So sketch the graph of f of x and find the area. Bounded between 4 and 8. And the x-axis. Okay, so let's first graph that. I notice this is a linear line. If you want to rewrite it, we can write it as in the form y equals mx plus b. So just rewriting the order, this is negative x plus 3. I notice my slope is negative 1. I can write this as negative 1 over 1, which gives me directions on how to get points from other points on the line. And I know my y-intercept here is at 3. So putting that together and graphing. So y-intercept at 3. Slope is negative 1, 1. So if I go down 1, I'm running 1 to the right, positive direction. Down 1, 1 to the right. I'm going to need some more points. I'm going to 8. So at 4, I have negative 1. 5, I have negative 2. 6, 7, 8. So 8, what am I going to have is negative 5. Okay, so it told us they wanted us to sketch our graph, which we did. And it told us it wanted us to find the area between 4 and between 8. And the x-axis. So we're wanting to find this area that's falling in here. Well, notice you have 2 separate triangles in there, right? You have this triangle, the bigger one. And then we're trying to cut out the smaller one in here. So we want the area of the big triangle minus the area of our small triangle. Okay, so let's look at the area of the big triangle. Well, this is base times height, 1/2 times base times height. Okay, so if I look at this whole total distance, this is actually from negative 3 to 8. So the whole base is 5. So 1/2 times 5 times the height. So this height in here, well, when we had negative 8, if you plug that into your equation, 3 minus 8, that's negative 5. So this hits at negative 5 down here. So that means that this length in here is positive 5. So this is 25 halves. I'm going to keep that as a fraction so that it's easier later. Okay, so now I have to look at the area of my smaller triangle. Well, that's that distance in here. This is from x equals 3 to x equals 4. So this little triangle, this length in here is 1. And I'm going from my x-axis down to when x is 4. So if I plug in that, that is 3 minus 4 is -1. So this length in here is also 1. So the area of my small triangle is 1/2 times base 1 times height of 1. So this is equal to 1/2. So looking at this area that we wanted to find, which is just in here, we have 25/2 minus 1/2, which is 24/2, which is 12. Units, whatever our units is squared. So let's do the same thing, but now let's evaluate the integral. Not the same thing, I guess that's not the same thing. So now we want to look at the integral. Lower bound was 4, upper bound was 8 of our function 3 minus x dx. Okay, so looking at this, we're going to take the antiderivative of 3 and the antiderivative of -x. So antiderivative of 3 gives you back 3x minus the antiderivative of x. So add 1 to our exponent, divide by our new exponent. So x squared over 2. And we're evaluating this from 4 to 8. And so we want to look at the antiderivative evaluated 8 minus the antiderivative evaluated at 4. So 3 times parentheses minus parentheses squared over 2. So plug in 8 minus the whole quantity. So put brackets f of 4. So now we're going in and wherever we see an x in our antiderivative, plugging in 4. So we have 3 times 4 minus 4 squared over 2. So looking at this, we have 24 minus 8 squared is 64 divided by 2 minus bracket. So 3 times 4 is 12 minus 4 squared, 16 divided by 2. So 24 minus 64 divided by 2, that is 32 minus bracket. This is really 12 minus, well, 16 divided by 2 is 8. So 12 minus 8 is 4. So this is really 24 minus 36, which is -12. Okay, so remember I said that if we're thinking about area, we have to worry about, is our function above or below the x-axis? And so notice that we got -12. So this is almost correct for our area if we looked at the absolute value of that. So for area, we got the negative of that because it fell below the x-axis. And so if you are trying to find the area under the curve, so let's say find the total area under the curve. you have to take the absolute value of the piece of the graph below the x-axis. So in our case, we would have had to look at, this is really the absolute value of -12, which is 12, which is exactly what we got for the area when we used some geometry. So let me pull out some more. So let's look at the following definite integral. What if we were going from 0.5 all the way up to 1? And this is of the function p cubed minus e to the 4p dp. And the directions just say evaluate the following. The following definite integral. Okay, so just kind of recall there was a rule for E if that power wasn't just that variable. So if you had e raised to the kx dx, this was equal to the original e divided by the k. Technically, I have to put that c there because I don't have bounds on that, but we're not going to over here. Okay, so now we can take the antiderivative. So antiderivative of p cubed, add 1 to our exponent. So I got p to the 4th, divide by my new exponent 4, minus, so the antiderivative of e to the 4p. So that's e to the 4p, all divided by 4. And we're evaluating this from 0.5 to 1. So you're going to go in, and wherever you see a p, you're first going to plug in 1. So you have 1 to the 4th minus, or divided by 4, e to the 4 power times 1, all over 4. Minus, we need brackets. Now plug in 0.5 wherever you see a p. So you have 0.5 raised to the 4th divided by 4 minus 4, e raised to the 4 times 0.5, all divided by 4. So simplifying, we got 1/4 minus, this is really e to the 4th divided by 4. Let's distribute that negative. So this is really minus, so 0.5 raised to the 4th power, which is 0.0625, all over 4. But a negative times a negative, so this is now really plus e to the Well, 4 times 0.5, that's 2 all over 4. Okay, so we can combine like terms. Let's see what they left theirs in, they put theirs in decimal form. So 1 minus 0.0625, that is going to give us 0.9375 all over 4 minus e to the 4th over 4 plus e squared over 4. So I can take that answer, I could subtract off e to the 4th. I'm just going to combine my numerators. Plus e to the 2, e to the 2, divided by 4. So if you do this, you get approximately negative 11.57. So if you get the answers negative, what can you assume about the graph? Can we assume that that whole graph is underneath the x-axis? Not necessarily. We could have a piece above and a piece below. But if that was the case, then the area of the piece below is larger than the area of the piece above. But I know that it is falling below the x-axis because I'm getting a negative answer. Okay, so we can use this fundamental theorem of calculus, this definite integrals rules, and apply it while we're using U-Substitution to help us integrate. The thing is, there's 2 different ways to do this. If we're looking at definite integrals and we're using U-Substitution, we either need to change our bounds on our integral right away, or when we are finished, before we plug in our numbers, we have to use our U-Substitution, plug that in, and then we can use our original. So it's up to you, and I can show you 2 different ways. I used to think that doing it later was easier. Now I think that doing it at the beginning is easier. So it really just depends. You'll get the same results. So let's look at one where we have to apply U-Substitution in order to integrate. So what if we're looking at the integral from 1 to 4 of -3, all divided by 2x plus 1 quantity squared dx. Okay, so in order to integrate this, we need to use U-Substitution. Okay, so we got to figure out what we're going to let U be. Well, I know if this was -3 over U squared, I can then use my general power rule when I'm doing the antiderivative. And so if I choose what's inside of the parentheses in the denominator, then, and I take the derivative of that, it's not going to leave me with any x's. And I don't need anything, any other x's canceled out in here. So if I let u equal 2x plus 1, this is where we had to take the derivative of both sides. So the derivative of u is 1 du, or just du, equals the derivative of 2x plus 1. So derivative of a 2x is 2. derivative of 1 and 0, and then we took it with respect to x, so we put the dx. We wanted to go back in and we wanted to replace what we just did. And so we're going to rewrite this. And I'm going to leave my bounds off for here right now. It might help if you put question marks here for a second, because it's totally wrong if we put in the 1 to 4. So this is -3 all over. We chose that parentheses to be u, so u squared, and then dx. Well, dx, if we divide both sides by 2, we can say dx is the same thing as du over 2. So dx is du over 2. If we change our bounds now, you would plug in your x values into what you chose u to be and solve for u. So you would plug in the bounds into what you chose u to be. Okay, so basically we want to look at when x is 4 and we want to look at when x is 1. What would u be in that case? Well, we had chose u to equal 2x plus 1. So this would equal, u would be 2 times 4 plus 1. So this would give me 8. So when x was 4, which was my top bound, we're now going to use 8. Now, if we plug in our bottom bound, 1, for u. So doing that, we get u is equal to 2 times 1 plus 1. So we get u is equal to 2 plus 1, which is 3. So our bottom bound is 3.
Shouldn't the top bound be 9?
Whoops. 2, 4, yep. 8 plus 1 is 9. Okay, so the benefit of changing the bounds now is when we take the antiderivative of this, we do not have to go back and do our U-substitution. Go back in and plug in what U was. We can just plug in those substitutions as to U. If we didn't plug in and we kept our bounds the same, that 1 to 4, when we did our integration, we'd have to go back in, plug in what U was in terms of X, and then we would use those numbers we started with. So that's the difference between the two there. Okay, so now I'm just going to rewrite this. I'm going to pull my -3/2 out in front because that's a coefficient. I'm looking at this from 3 to 9. And I'm going to bring my u squared that's in the denominator up into the numerator. So this is really u to the -2 power du. So we have -3/2. So the antiderivative of u to the -2. So add 1 to our exponent. Well, -2 plus 1 is -1. Divide by our new exponent of -1. Because we changed our bounds before, we can just plug in 3 to 9. We can leave that -3/2 out front if we want. We could actually pull out if we wanted that -1. Well, it's not actually. So let's rewrite this. This is the same thing as -1 over u. Bringing that u to the -1 exponent down. Okay, so plug in 9 wherever you see a u. So we have -3/2 all times -1 over u, which is 9, minus the -1 over 3. So this is -3/2 all times -1/9 plus 1/3. I notice I need a common denominator, and so we can rewrite that as 3/9. So I have -3/2 all times, well, -1/9 plus 3/9 is 2/9. I notice my 2's cancel. My 3 goes into itself once, and my 3 goes into 9 3 times. And so we're left with -1/3. Can you guys hear the whistling in the background?
I didn't notice it.
You did or did not?
I didn't.
Okay. As long as you guys aren't hearing it. It's a little distracting to me, and I was going to scream out to the person who's doing it. But if you guys can't hear it, then that's okay. They're just happy, so they're whistling. I won't take away their happiness, maybe. Okay. Actually, I will. Hold on while I scream. Let me pause. Okay, so that was us doing it where we changed our bounds at the beginning. Let's go back real quick. And let's say we got to the point where we had, we plugged in our u value. Let me see. So if we had 1 to 4 of -3 all over 2x plus 1 quantity squared dx. I'm going to put here, if I don't change my bounds, just so we don't forget, we're going to put in here that x equals 1 now, because we're putting in u values. So x equals 1 and x equals 4. And now if we go back in and we did that substitution, so this was -3 all over u squared. Du, which was that, or dx, which was the du over 2. So we would have integrated it the exact same way. We would have seen that when we took the integral, what did we get? We had that -3/2 out front. We had -1 over u. And so before we can evaluate this, and this was x equals 1 and x equals 4. In this case, we have to go back and rewrite u in terms of x. So doing that, we have -3/2. This is -1 all over u. We had chosen u to be the 2x plus 1. And now we're evaluating this from x equals 1 to 4. I guess I don't really have to put the x equals now. So now if we go back in and plug in 4 wherever we see an x, so this gives me Actually, I'm going to write that as positive 3/2 out front. I have 1 all over 2 times 4 plus 1. And then I'm going to have minus, now plugging in 1 wherever we see an x. This is 1 all over 2 times 1 plus 1. Just to show that this was positive now. This is equal to 3/2 all times, this is 1/9. 2 times 4 is 8 plus 1 minus, this is 1/3. Need a common denominator. And so this is equal to 3/2. Well, 1/9 minus 3/9 is negative 2/9. We can reduce, and this gives us our negative 1/3. So either way, you get the same result. One, you change the bounds right away, and then you don't have to worry about changing u back in terms of x, or one, you wait, do the integration, replace u in terms of x, and then you can use the original bounds. So I don't know, whatever one you feel is easier. The problem is with the second way we did is if you forget about changing, don't change u back in terms of x, it's wrong. So. Okay, so let's look at another example. So this one's actually going to ask us to find the area under the curve. So use definite integrals to find the area between the x-axis and f of x over the indicated interval. Check first to see if the graph crosses the x-axis in the given interval. Okay, so we're going to find the area under the curve. For the given value of f of x. Between the bounds. And the x-axis. Okay. So we need to calculate for any area that falls underneath the curve. Okay, let's look at what if you were looking at f of x is equal to 1 minus 1 over x. And we want to look at it between the bounds of e to the negative 1 and e. Okay, so we want to look at what the graph of 1 minus 1 over x is. A couple things that we have to be careful of. We need to make sure that that function is, we need to make sure that function is continuous on our bounds. So I only noticed one problem for f of x for the domain. X cannot be 0. But if you look at that, e to the negative 1, that's just 1 over e. So 1 over 2.718. That's a positive number to about 2.718. So 0 is not in that bound. So f of x is continuous on the bound between e to the negative 1 and e. We also need to find out, is this graph above or below the x-axis? And is it above or below the x-axis for the entire bounded interval that we're looking at, or is it crossing somewhere in between? So does f of x fall above or below the x-axis between e to the negative 1 and e? Okay, so looking at that, I can see that I can solve for my x-intercept. I can set my f of x equal to 0, my y value equal to 0, and solve for x. So let's look at when is 0 equal to 1 minus 1 over x. I don't like that I have x in the denominator. I know I can take care of that by multiplying both sides of my equation by my least common denominator, which is just x. So x times 0 is 0. And this is equal to, well, distributing my x. So 1 times x is x minus, well, the whole point of me distributing this is so those x's cancel and I don't have the fraction. So 0 is equal to x minus 1. So now I get that x is equal to 1. So I know I have an x-intercept at 1. I also notice that 1 falls in between e to the negative 1 and e. So I really need to see, is my graph falling above or below the x-axis? And without graphing that or pulling up some graphing calculator, I can do that by just testing a value between e to the negative 1 and 1, and a value between 1 and e into my original function to see if it's positive or negative. Okay, so we have this e to the negative 1, because that's our bound. We have, which is 1 over e, which is, let me just approximate what that is. So 1 divided by e is about, let's just say it's about 0.4. We have 1 in here, and we have our e. 2.718. So let's look at f of, so a number that falls in between these two. So how about x equals 0.5 into our original function and see if it's positive or negative. Well, our original function, that was 1 minus 1 over x. So 1 minus, oops. So 1 minus 1 over 1/2 or 0.5. Keeps on jumping. That gives me 1 minus 2, which is -1. And so I know that this is below the x-axis. It's possible that the graph comes up, touches the x-axis there, and goes back down. So I really need to check a point in between the 1 and the 2.718 just to see if it's positive or negative. And so how about 2? If we look at f of 2, well, this is equal to 1 minus 1 over 2, which is equal to 0.5, which is positive. So this is above the x-axis. Because we want to find the total area, we want to take into account that when we look at the definite integral of the piece underneath the x-axis, we're going to get a negative, and we need to take that and put absolute values around it. So this is how we're going to write it. So we had the integral from e to the -1 half order of e of 1 minus 1 over x dx. So we're going to break this up into 2 separate intervals. One falls in between there. So we want to look at our lower bound, e to the -1, all the way to 1. Of our function 1 minus 1 over x dx. This was the piece below the x-axis, so we need to take the absolute value of this piece. Plus, now we're going to look at the integral. So starting at 1 and going to e of our original function, 1 minus 1 over x dx. And so now we can integrate. I notice that I can integrate both of these without using U-substitution. 1 over x is a special case. That's where our power is -1 if we brought that up. And so we can't use the general power rule. So the antiderivative of x is x minus, so remember the antiderivative of 1 over x, that was the natural log of x. I don't have to worry about those absolute values around this x piece because these are both positive numbers. So I'm looking at that going from e to the -1 to 1. Plus, then I'm looking at the antiderivative of this piece. Well, we just found it. That's the same thing as we had over here. So this is x minus natural log of x. And this one is going from 1 to e. So we're going to go in and plug in our numbers. So plugging in 1 wherever we see an x, we have the absolute value of 1 minus ln of 1 minus the whole quantity, now plugging in e to the -1 for x. So e to the -1 minus natural log of e to the -1. And our absolute value plus, now we're going to do the same thing here. So plugging in e for x, we got e minus natural log of e minus the whole quantity, now plug in 1 for x. So 1 minus ln of 1. Okay. So this gives me 1 minus, well, the natural log of 1 is 0 because e to the 0 power is 1. So this is, and then we need to distribute this negative sign. So this is e to the minus e to the -1 plus, okay, so natural log of e to the -1 is just the exponent. And the exponent of that is -1. So just looking at this piece, I have 1 minus 1 cancels, minus e to the -1. But the absolute value of e to the -1 is e to the -1. Okay, so let's finish off that piece over here. So this is going to be plus, so this is just e, minus natural log of e. So this is saying e to what power is e? Well, that's 1. So -1. Got to distribute the negative. So -1 plus so this is saying e to what power is 1? Well, e to the 0 is 1. So right here, I'm going to bring down my plus e. -1 minus 1 is -2. I know that's a positive number because 2.718 minus 2, that's a positive number. So I'm okay. That was above the x-axis. This is plus e minus 2. So I'm not sure if they wanted an approximation or not. And if they do, and we could rewrite that e to the -1 as 1 over e plus e minus 2. So that would be the exact answer, and 1.086 is the approximate. So if we graphed that original function, which is way back up there, from 1 to -1 over x from e to the -1 to e, we found that part of it is above the x-axis, part of it's below the x-axis. The piece below the x-axis, if we're finding area, we have to put those absolute values there. And then we had to break it up as 2 separate integrals, the piece above and the piece below, and then sum them. So there is your fundamental theorem of calculus and definite integrals. There is one other section I did want to cover. I don't know if I am actually going to cover that, which was area between 2 curves. I'm thinking that we pretty much finished off the material that we're going to do for this semester. So I think this is where we're going to end. What I went over today was 7.3 and 7.4. 7.3 does not have very much homework, I believe. It's pretty much looking at areas of shapes under a curve using areas that you know how to use. When I made that assignment last semester, we were short on time too. So unfortunately, I was speeding through like I did this semester at the end. So homework will be due on Tuesday. You have a test. The 3rd exam is going to be Thursday next week. It will be on my math lab, similar to what we had done in the past, the last test. And then your final is the following week, which I have it written down. Your final is May 14th, and it is from 10 to 11:50 a.m. So it just happens to be the same time our normal class period is.